All right, starting light and breezy with just combining two radicals here. Notice we don't have the same radicand, so at first glance we're like, oh, can I even do this subtraction? We always want to start by seeing if we can simplify. We have the same index for both of these radicals. They are square roots. So if you have your perfect squares and cubes worksheet, that's going to have a list of perfect squares on it in the end of the second power column. So it's worth taking a second to check, do 27 or 12 have perfect square factors? In the case of 27, it does. 27 can be broken up into 9, that's our perfect square, times 3. Again, 9 times 3 is 27, that's where those numbers are coming from. The reason we're picking 9 is because it's in the perfect squares column. The square root of 9 is 3. The root 3 is just coming down. Square root of 3 is not a nice number, so we just leave it alone. And we don't want to lose our coefficient, the number up front. So there are a whole lot of 3's in that left term. Once we jump over to the right term, well, 9 doesn't divide evenly into 12, but 4 does. So we can break 12 into the square root of 4 times the square root of 3. Again, the reason we're picking 4 is because 4 is a perfect square. The 3 is there because 4 times 3 is 12. Square root of 4 is 2. Like before, the root 3 is just tagging along for the ride. And once again, we don't want to lose our coefficient, the 2. Now, this was a subtraction problem. Nothing has changed that. It is still a subtraction problem. So we've gone ahead and broken up all of our radicals. We can clean this up. Right now, it looks pretty messy. 3 times 3 is 9. So we have a 9 root 3 minus 2 times 2 is 4, 4 root 3. So we have 9 apples. You take away 4 apples. That means we have 5 apples remaining. Unfortunately, instead of delicious apples, we have root 3's. Not quite as tasty, but the same process applies. So that root 3 isn't something we saw in our original problem. We needed to simplify in order to get that. But notice once we were able to simplify those radicals, we saw those root 3's come out. Once we knew we had two terms with a root 3 in them, we were able to put them together. Jump into the second example. These are now cube roots. That little 3 there is telling you it's a cube root. So on your perfect squares and cubes cheat sheet, you want to be looking at the cube column, n to the 3rd power. So none of these are perfect cubes, 54, 2, and 16, but we can certainly break them up and find those perfect cubes. Let's start with the 54. 54 can be obtained by doing 27 times 2. 2 is not a perfect cube, nor is it going to have a factor in the perfect cubes list other than 1, and breaking 2 up into 1 and 2 doesn't help us much. 16 we can break up. 16 we can break up into 8 and 2. And if you're looking at this, not quite sure where to put the negative, note that the goal is to get those like radicals. Since I have a 2 in the first radical, a 2 in the second radical, I really want to keep that 2 in the third radical. So I recommend bringing the negative down with that 8. Adding in those cube symbols really quick. Now we have something that we can work with. The cube root of 27 is 3. And again, if you're kind of not comfortable with your perfect cubes, I recommend having this sheet out here in front of you. 27 is a perfect cube. And if you're looking to the left, you can see that the cube root of 27 is 3. This sheet works both directions. You can use it to say that 3 cubed is 27, or you can use it to say that the cube root of 27 is 3. So make sure you have this sheet in front of you. It will be super helpful for those problems. So the cube root of 27 is 3. We still have a cube root of 2 tagging along, and just like the previous problem, we don't want to lose that 3. Jumping over to the middle term, there is a subtraction. We don't want to lose a subtraction, and that is a 2 Cube root of 2, that should have been 3. And then last but not least, we have our next term. Now this started off as a plus problem, but because we have this negative 8, I'll highlight that one in yellow. Because we have this negative 8, the cube root of 8 is 2. The cube root of negative 8 is a negative 2. So that's going to make this a minus. It was originally a plus. It's going to switch to being a minus because of the 2 that comes out of the cube root of negative 8. We still have a 7. The cube root of negative 8, again, is the negative 2. We've already taken care of the negative. And the cube root of 2 coming down from there. So there's a lot more going on in this problem than the previous one. A bit of cleanup. 3 times 3 is 9. Switch colors here. The middle term, there's not a ton we can do. And then our last term, 7 times 2 is 14. So putting these together, we now have, missed the 2 there, we now have like radicals. Notice that all 3 of these are cube roots. They all have a 2 underneath them, so the radicands match, the indexes match. We can put these together. So we can go back to just looking at the coefficients. 9, minus 2, minus 14. So if we have 9 and we take away 2, that gives us 7. And then if we have 7 and we take away 14, that's going to be a negative 7. You could use a calculator there if your mental math is not as strong as you would like it to be. But again, the way I got that negative 7 is 9, minus 2, minus 14, just looking at the coefficients there. It's probably long enough for one video, so take a second, look at your guided notes. If you have a question on any of these numbers or anything is coming from anything else, please raise your hand. Next video, we'll take a look at a much more difficult one.